Hello grade 12s, this is our second video in our series on reaction rate. Not such a demanding chapter as, for instance, energy and change, which is a good nice little breathe before we get to equilibrium in the next chapter. So we're going to still continue with a little bit of theory, but before we do that, let's just quickly start with the questions that I posted in the previous video. Most of them are theory questions. It's not hard thinking questions. So in this case, this is stuff that you mostly have to learn. It's not development of cognitive skills. So I guess it isn't the greatest sin if you haven't done the work before you watch this video. It's not as great a sin as with the Doppler effect or the energy sums. Although I do encourage you, go and sit and try and do these things on your own so that you know that you understand the theory. Okay. This example of the exothermic reaction, easy peasy, it's an exothermic reaction because it's got a negative delta H. And if I calculate the potential energy of the products, it's final energy minus initial energy will give me my delta H. They told me delta H is minus 200. They told me the energy of the reactant is 600 and the reactant is initial, so they'll leave me with X is equal to 400 kilojoules. So that was an easy 6 marks in the exam with no sweat. Okay, and then they asked me at 1.3 to draw the diagram. They told me that the potential energy of the reactants is 60, so I could start there. Oh, there it goes. And they told me the activation is 40, the energy is 40. That's why I could just add these two and get up to 1,000. And then I had to sketch the energy diagram. This one you kind of learn. It's the one for the endothermic reaction, the exothermic reaction, sorry. And I have delta H, that is the difference between the beginning and the final energy, which I calculated in my previous sum as well. So this is quite a nice graph and a nice easy 4 marks. A catalyst is added. How will it influence activation energy? It lowers the activation energy. Okay, so let's get to the new work. In this video, we will specifically look at the calculation of reaction rate, which is a very practical thing that is done in a laboratory under certain conditions. Now here I have 2 setups of different reaction rates that we can have. You can see over here I have something like zinc that's reacting with an acid, let's say hydrochloric acid, and it's giving me a gas. So if I want to measure the reaction rate, I need to measure the change in the concentration or the volume. Either it can be the concentration or the volume or the mass, we'll get to that, of the gas that forms over the specific time. So in this setup, I'll also need a stopwatch. And then what's going to happen as the reaction progresses, this syringe will automatically go out so that the volume of the gas increases because more gas is forming. And then literally what you do is you start with, let's say in this reaction, I'm going to start with no gas. So my initial concentration is going to be 0. And then I measure my final concentration and the time that it takes to reach that final concentration there. And that is how I do this. So typically in the exam, they might give you a setup. I think something like this was in an exam paper and something like this also came from an exam paper. Now let's see what's happening in this question over here. Here you can see I have some marble chips. They told me this is marble chips, and I've got hydrochloric acid. So this is reaction between calcium carbonate, which is marble chips, and that will result at the end of the day in CO2 gas that is being given off in this reaction. So now what I'm going to look in this reaction is why is the mass going to decrease? Any idea? Because in a reaction we know that the mass must stay constant. Now the mass in the reaction is not decreasing. The mass in the reaction is constant. But this is cotton wool. This is not a solid stopper over here that completely do not allow any gas to escape. If this was, this whole thing would burst now, because your gas would form and there's no way in which the volume increases, so you'll get into problems. So what you could typically do, you can have a setup like this one as well, combined with this one where you have your marble chips, and then you can measure your reaction rate either as the change in the mass of the marble chips, because the marble chips are going to become less, and it is being converted into gas that is escaping, and that is why the mass is decreasing. Okay, so it's not the mass, the decrease of mass in the reaction, it's the decrease of mass in the reactants, which means there will be an increase in mass of the products. Okay, just as a practical matter. So often in the exam they might give you a setup like this, and they might ask you questions. They might ask something like, why is mass decreasing, like I just explained, or they might ask, why can't you replace this with a solid stopper? So you have to think practically of how these experiments could work. Our exam guideline expects the following from us regarding calculating the rates and reaction factors. Now, the factors we're going to concentrate on in the next video. In this video, we are just going to look at the definition of a reaction rate and how to calculate reaction rate. Reaction rate is defined as the change in concentration of the reactants or the products per unit time. Can't be the change of the reaction, because there's no mass change in the reaction, mass is conserved. So it's either the products or the reactants, the change in time. The calculation of the reaction rate is as follows. The rate is equal to the change in concentration divided by the change in time. This is a very interesting reaction. In fact, or equation. In fact, I'm very hesitant to say there's mistakes in the exam guideline document, but as far as I know, this should be rate is equal to minus the change in concentration divided by the change in time. And just to confirm my suspicion, I had a look at the 2019 exam, and there was a calculation. I actually have that calculation in this video as well, of the reaction rate. And in their calculation and in the memo, they state the rate is equal to minus delta C over delta T. But what's interesting to me is they also accepted in that calculation the negative answer if you use this formula. Now, I don't know if it is because the formula is wrong in the exam guideline. I just don't know. But I would advise you rather to use the formula rate is equal to minus delta C over delta T. And these questions are not only limited to moles per decimeter per second, moles per decimeter, that's your concentration per second. They could also ask you for grams per second or volume per second. They can be in terms of mass or volume or the number of moles, depending on the calculation. Just keep your heads about you. These are not difficult sums. Also a relative easy 3 marks in the exam. Reaction rate sums can be quite a lot of fun, and you can actually calculate it very, very specifically. And there was a group of students at a university, I can't remember which one now, which actually each of them made a solution that had to react in a specific time, and they used the iodine clock reaction. Now, what is spectacular about this reaction is for a long time you don't see a thing, but then all of a sudden the color changes. And then these students had to make these color changes fit in with a certain rhythm, and they did. And I'm going to include this video quickly that you can have a look at that. How nice you can work with reaction rates, how very precisely one is able to calculate them, just as a breather. So let's get to the calculation of our reaction rates. The average rate of calculation is the change in concentration divided by change in time, or minus delta C over delta T. Remember, delta C is always final minus initial, but now because I have minus in front, I can say the concentration initially minus the final concentration, divided by the time at the end minus the time in the beginning. But remember, they told us we can calculate reaction rate in different ways. We can also have a change in mass over the change in time, which we calculate in the same way, as well as the change in volume over the change in time. Usually, these sums are about 3 marks. Usually 1 mark for the equation, 1 mark for the substitution, and 1 mark for the answer. Okay, and I can also have a change in moles divided by the change in time. Now let's just look at a quick example. This is an example from the 2019 question paper. So an antiacid has a mass of 2 grams, is placed in hydrochloric acid. After 30 seconds, the mass of this tablet was found to be 0.25. So this is a calculation that we have to calculate the rate of the reaction in change in mass over time. So as you can see, I just take the initial mass minus the final mass over the time it took, and then it will give me my answer in grams per second as a rate. Okay, so really not very difficult sums, a nice and easy breather in the exam. Okay, now often with reaction rate they give you a table, a graph like this, and I'm just quickly going to explain where the reaction rate, the calculation for reaction rate fits in this. Now if we look at this reaction, this graph, I just put in this equation, since I see they've used this equation in the graph to give you an idea of what they are showing you. Now, if you look at the blue line over here, initially there was nothing at the beginning, like here. This what I have here is the same reaction. Doesn't really matter which one is which. Let's pretend the pinkish balls is hydrogen, and the bluish ones, they are iodine. Okay, so now you can see in my container, right at the beginning, there was no hydrogen iodide. So there's no mixture of pink and blue balls. Okay, so right at the beginning, my concentration of HI there is 0. But and my concentration of my hydrogen and iodine is very, very high. So if we look at these two different lines, the one line, the red line, shows me how my concentration of my reactants changes as time goes by. Okay, so the gradient of this graph will be my reaction rate for the change of the reactants. This one shows me the rate at which my products are forming. So this will be the reaction rate for the forming of the products. Now you can see the reaction rate for the reagents is negative, okay, because it's decreasing in the amount. You can see if you think of gradient, this is a negative gradient and it's decreasing. Initially the gradient is a bit more than it finally is, but if you look at the forming of the products, you can see initially this is definitely a positive gradient, but initially the gradient is much steeper than later on in the reaction. Okay, so there you can see this line, the gradient of this line, which is the tangent to the curve, is much steeper than the gradient over here. And the gradient over here is a bit steeper than the gradient over there. So here you can see the reaction rate, as time goes on, the reaction rate decreases. The reaction rate is actually just the slope or the gradient on the slope. Okay. Now, as a quick demonstration, I made this video to quickly show you what happens in the vase. So now I have my hydrogen and I have my iodine, and now the reaction happens, stop. And you can see once the reaction is complete, the entire concentration of hydrogen and nitrogen now is 0. There's no hydrogen and no nitrogens. There's only hydrogen iodide. Now, people, this analogy has a lot of flaws. For one, you can see some of the dots aren't moving and others are just joining them. And we know for a proper reaction rate to form, we need collisions and we need effective collisions to make sure that you understand that, I'm going to send you a very nice video that I found on YouTube on just how reaction rates can be explained by dating, which I find fascinating. Okay, so I just wanted to show you how you look at this reaction. What is the type of image that must form in your mind? You have your reactants initially and no products. And then the reaction occurs and now you have products and no reaction. And the time that it takes for all of these atoms to move around, that is the time that your concentration is changing, and that is the time that you're going to use to calculate your reaction rate. Okay. Measuring of the reaction rate, we talked about this a bit in the beginning. How do we actually measure this? Well, in this case, it's the combination of the two experiments that I showed you initially. We have some kind of stones, probably some kind of carbonate that is giving us a gas, which is CO2 gas. And then you can measure the volume of the gas over time. So every second you can take a reading and see how this thing is going to change. So you need a syringe that can move freely. And then from your results, you are able to draw a graph. It is a good idea to know the different apparatus used in an experiment like this, because at times they have in the exam asked you some of the names. So some of the names. Oh, I keep on mixing in some Afrikaans here. Ugh, sorry. Forgive me for that. So over here, for instance, one of the things that you can look at is the fact that we call this one a conical flask or an Erlenmeyer flask. There's your gas syringe. This one over here is your retort stand, or you can just say stand and clamp. That's fine. But this is more or less a setup that you can use in this graph. It's very important that you don't only think of this as abstract theory. These are real experiments happening out there, as was nicely explained by Tchaikovsky, by that reactions that happened on the song previously in this video. Okay, there's another way that we can do this experiment by having it on a scale so that we can have a mass change all the time and measure that. You have a cotton wool that allow the gas to pass through. Otherwise, if it didn't allow the gas, then you wouldn't have any decrease in mass over here. Then your mass would stay the same all the time. But then you can take a graph of your mass divided by time, and you can see initially the gradient is quite steep, but then as time goes on, this gradient becomes less and less steep. Okay, we have 4 sums in which we can calculate the reaction rate. Somebody asked me to include the mark allocation, which I neglected to do. Sorry for that, but usually it's 1 mark for the substitution of 1 mark for the equation, 1 mark for the substitution, and 1 mark for the answer. Okay, so here's your first problem and your second problem. Both of them are the change in mass. You have 5 grams magnesium in hydrochloric acid. I suggest you pause the video to quickly do this one. There's 2 more coming. Another one, but this one you have to calculate the reaction rate. Oh no, you have the reaction rate. You need to calculate the time. Pause the video and quickly do this one. And then the last one is slightly more difficult. They give you the mass, but you have to calculate in moles per second. You have to calculate the reaction rate of the reactants, the decrease in mass of the reactants. Okay, have fun. See you next time.